Oke, kembali lagi dengan saya Widianto. Kita lanjutkan bab kritik. Kita baca chapter 1, pitch, frequency, and musical scale. Kita ada dari Cook. In nature itself, a single note sets up a harmony of the sound, and this harmonic series has been unconscious basis of Western European harmony and the tonal system. The scientific study of music was put on a firm footing in a work of Hermann von Helmholtz in the middle of the 19th century. His masterpiece on sensations of tone is still worth studying today. In this chapter, we describe Helmholtz's ideas to show how they provide a rationale for musical scale. Nah, sini nada, frekuensi, dan tangga nada. Di alam itu sendiri, satu nada tunggal sudah harmoni dengan sendirinya, dan deret harmonik inilah yang menjadi dasar secara tidak disadari bagi harmoni musik Eropa Barat dan sistem tonal. Kajian ilmiah tentang musik mulai memiliki landasan yang kokoh melalui karya monumental Hermann von Helmholtz pada pertengahan abad ke-19. Karyanya yang terkenal On the Sensation of Tone masih sangat layak dipelajari hingga hari ini. Dalam bab ini, kami menjelaskan gagasan-gagasan Helmholtz dan menunjukkan bagaimana gagasan tersebut memberikan dasar rasional bagi pembentukan pitch and frequency. There is a close connection between pitches in musical tone and the mathematical concept of frequency. In the 19th century, Helmholtz did an experiment with tuning forks. He attached a pen to one of the sides of a tuning fork and drew the fork across a piece of paper while it was sounding a specific pitch. The vibration of the pen stretched out a simple waveform. We will refer to it as a pure tone waveform. The most fundamental aspect of a pure tone waveform is that it repeats itself periodically. In physics, the distance from one peak of the wave to the next is called its wavelength. Another term for wavelength is cycle. We have Mach 1 cycle for the pure tone waveform figure 1.1. The number of cycles of pure tone waveform that occur in 1 second is called its frequency. We have this formula for frequency. Frequency is equal to number of cycles of second. The unit of cycles of second for measuring frequency is also called Hertz. This is short for Hertz. Another German physicist who did fundamental work in study of frequency. For example, if the cycle shown in figure 1.1 has a time duration of 0.05 seconds, then the frequency of the pure tone waveform is 1 of 0.05 equal to 40 Hz. Nowadays, with digital technology, we can record a representation of sound wave from a tuning fork as a future demonstration of Helmholtz's idea. In figure 1.2, we show that the plot of the digital waveform recorded from a tuning fork. This tuning fork was designed to match the mix for the key of middle C on a piano. As described in the In the caption of figure 1.2, the frequency for the pure tone waveform produced by the tuning fork is 2062 Hz. The maximum Y values of waveform are approximately salah ya, 262, ini 5000, and the minimum values are all approximately 5000. This number 5000 is called the amplitude of the pure tone. The larger a pure tone amplitude, the louder the volume of this sound. To conclude our analysis of pure tone from tuning fork, we look at an extremely important method for displaying the single constant frequency of the pure tone over time. This method of display is called spectrogram. Oke, ini kita lihat ya. Figure 1.1, illustration of the famous experiment of samples. A pen is attached to a tin of tuning fork. As tuning fork is struck and drawn across a piece of paper at a uniform speed, the pen traces out pure tone waveform. Distance marked between the two peaks of waveform is called cycle. Figure 1.2, left, waveform from recording of tuning fork with one cycle marked. P is equal to 0.00382 seconds. Frequency is about one cycle of 0.00382 seconds is 262 Hz. So note from tuning fork is middle C. Oke, dari sini. Oke. Right, yang kanan, amplitude for waveform. The height of the pipe at frequency 262 Hz is approximately 5000. Oke, kita lanjut. In figure 1.3, we show a spectrogram of a recording of sound from the tuning fork discussed above. We will describe how this spectrogram is used in chapter 4. We are using it now because it provides such an easily interpretable and compelling picture of the frequency content of pure tone. The single bright horizontal band in the spectrogram is centered on the single frequency of 262 Hz that we found for this tuning fork pure tone. We have now shown that there is a definite connection between frequency and pitch. For a pure tone from a tuning fork, there will be a single precise frequency for its waveform. Music, of course, is played on musical instruments rather than tuning fork. So we now turn to the questions of frequency and pitch for musical instruments.